Hello everybody. So here we have again two ones installed, the same number of oscillators, so 300 for the first one, first solid, and 200 for the second one, with the number of total energy is equals to 100. So we know that the most likely state would be the one where QA is equals to 60 and QB is equals to 40. Okay, so what is the number of total macro state at this point right here? Well, we don't have to calculate it. We can just go back in section 2.3 and look at the number that it gives us for the multiplicity. Let me go back so I can actually see it too. Okay, the table says we have 6.9 times 10 to the power of 114. All right. So what is the entropy? Well, we can just say entropy is equals to K ln of the multiplicity, this point at the most likely state. So we have K is equals to ln of 6.9 times 10 to the power of 114. We can break this up in parts. I'm just going to keep the K over there. ln of 6.9 plus ln of, actually, we can solve 114 times ln of 10. Okay, so I can actually plug it in my calculator. I'm gonna get K times ln of 6.9 is equals to 1.93 plus about 1.93, of course, plus 114 times the natural logarithm of 10, which equals to 331. So in this case, we're gonna have 331 plus 1.93, which is equals to 333. Honestly, let's round it up. K. Okay. And this is the most likely macrostate. Instead, for the least likely macrostate, which is where QA is equals to 0, our total number of macrostates is equals to 2.8 times 10 to the power of 81. So our entropy, again, ln of 2.8 times 10 to the power of 81 is equals to K ln of 2.8 plus 81 times ln of 10. Okay, so we have K ln of 2.8. Let me check what it is. We have 1.03. Of course, I'm always rounding, and 81 times 10 the power that 10. 81 times natural logarithm of 10 is equals to 180. 186.5. I'm just gonna keep it like this. Okay, so our entropy is gonna be equal to the addition of these two, which is equals to 187.5. We don't need to go that deep. Okay, so now, again, we have to find what is the entropy over long time scales. So in this case, we're gonna find the entropy of ln of total of all of the addition of all the entropies. So we would have to take the addition of all the entropies in all the cases. So it would be K ln of what you can see at the bottom of the table, 9.3 times 10 to the power of 115. So K, and then again ln of 9.3 plus 115 times ln of 10. So here we get ln of 10, sorry, ln of 9.3 is equal to 2.23 plus 115 times ln of 10 is equals to 265. So our result will be 267K. And this is the entropy over a long period of times. And if you look at it, this number that we just got, 267K, is slightly, oh, actually, I think I made a mistake earlier on. Which again, the 114 times ln of 10. Yeah, here I don't know what I wrote. I usually put 262, which are together means it's 264. Okay, I don't know what I did. So if you check it, it's actually slightly larger than the entropy at the maximum. Because again, we have the same shape for our entropy as we have for our macro state. We're gonna have something flat and then something like this. And this is our entropy, while for our macro state we would have something like this. As you can see, now actually that's pretty much the same value over there. As you can see, the blue peak is a little smaller than the S peak. However, this is just because the ln kind of smooths this peak right here. But we have the same functions. However, if we were to draw in scale, which I didn't want to do at first, we would have something like this. Because again, instead of having something like 10 to the power of 114, we just have 264 for our maximum. So here will be 10 to the power of 114, and here we have 264. Much easier to see and to use.